All right, so I am recording it, and then let's hope we have the record. So, okay, now we are going to turn into the tough topic, so to speak, because we are dealing again with the science way. Okay, maybe to say it tough would be, giving you like something. No, actually, it's not that tough. So, okay, let's see. We have talked about the non-size wave frame. So this time it's the size wave. When we are dealing with the size wave, you know that we cannot calculate the displacement due to size wave. Okay, you have seen the example in the morning that once you know the settlement of the beam, but you must know how much, right? You can calculate the fixed moment. We have the formula for it. But if your frame is going to the side like this, okay, say, if it dances like this, how much is this? In slope deflection, you solve for this, right? So it becomes one of your unknowns. But in moment distribution, you are starting everything with fixed moment. So when you don't know this, the formula that we just used for the calculation of the fixed end moment due to the movement of the joint becomes useless. So we can't. It means that because we don't know the exact amount of settlement, we don't know this, so we can't calculate fixed end moment. So we need to have one little extra step to allow us to solve the problem of the side sway. Think about Professor Hardy-Cross, who came up with this method. Well, how he could devise this thing. Okay, if you have side sway problem, here's what we need to do. Things like that. So first of all, you prevent side sway and you calculate everything. Okay. And after that, we need to assume the fixed moment due to side sway and calculate it. Because we don't know anything, so the best way to do it is to assume something. Okay? Assume the fixed moment due to side sway, any number, and then calculate the resulting moments and reactions. Okay? And then we combine the two cases. So basically, when you have a side sway frame, you can say that you have the moment due to, let's say, I'm going to give you the not non-symmetric loading. Let's say if we have the what do I have there? One moment, please. Okay, let's use this the same loading. Let's say I put some load here. That's clearly not symmetric. So this load will push your frame, wobbly to the side. This load will gives both fixed end moment and causes side sway. So I can say categorize a moment caused by this load into two categories. The first is just a typical fixed moment, and the second is the moment coming from side sway. Okay, I can easily calculate the first one by I can do so by preventing the movement like this. I add the support, and then I can carry out my procedure as normal. Okay, I can calculate the moment, whatever, but this will be the moment due to the load alone. Okay, moment due to load, side sway excluded. So you have a load here, and then case number 2, you're gonna have to assume how much this frame will sway. Please notice that in case number 2, we remove the load. Now the thing is, you assume the side sway because we don't know. But the key factor here is that, let's say you must know the relationship amongst the side sway. So if you know that this sway with delta, that has to be delta. So let's say if you assume that your moment here is, let's say this is your assume 80, assume number. If you assume that this is, let's say it's counterclockwise, right? So it's minus 80. You therefore must continue to assume that this is also minus 80. Because you know that if this is minus 80, this better be equal and go into the same direction. So this becomes the sorry. Let's try again. It becomes the corresponding value. Okay? Because you assume this minus 80, so you have to assume this minus 80. Because, you know, when you have this case, the moment must be equal, right? To try to resist the movement of your member. It has to be equal and go into the same direction. So if you say, I like number 80, I assume this 80, but actually I also like number 120. Can I use 120 here? No. You assume, but you must assume based on the proper rules of structural analysis as well. Here we go again. Your internet connection is unstable. How can it be? I'm sitting very near the source. Okay, let's do it again. One moment, please. Stop the share. Okay, let's try one more time. Okay. So it's back here. Okay. Again, if you begin with this number has to be the same because of the relationship of the end moments in the member. Okay. And next, because if this is delta, this is also delta, right? So it means that your assumed number here must also be related to this number. So likewise, if you assume this minus 80 and this is minus 80, and you have the same kind of column, this must be minus 80 and minus 80 as well. So the key is to assume with reasonable values and relationship. And then you carry out this analysis. Okay? And I think it's better that I give you some numbers so you get to feel it better. Okay? So let's say here, I'm gonna give you the case, the real case that I just drew. All right, so let's say we have the frame like this, and I have the load here. I took this number from the Imperial unit textbook. If you wanna prove it's okay, but it's in kip foot, okay? So this is 20K, and let's say this is 12 feet. This is 4 feet, and this is 20. So, okay, I have this situation. So I know I'm gonna have the side sway problem. So the first step is to prevent side sway. So that you can calculate the moment due to the load alone. I can prevent side sway by doing this. By adding the support here. Okay, and I can carry on and perform the moment distribution as usual until I get the final numbers. Okay, so the final numbers are like this: 11.8. This is 23.5. This is minus 23.5. Okay, this is 12.7. This is minus 12.7. And this is minus 6.3. Please note that the end moments shown here are final numbers. It means where you only get this moment after you're done doing the moment distribution. Okay, you need to do the moment distribution back and forth until you get these numbers. And once you get these numbers, you can calculate your reactions, right? In this case, it's a shear. So this will give you this value. Okay, this is 1.77 and this is 0.95. So these rate numbers are obtained after moment distribution. In other words, you obtain these numbers after you get these black numbers, okay? Do you notice one thing? Right here, sigma fx is not equal to 0. Which means after the calculation, you know that you need this equal to 0.82. Sigma fx is equal to 0 only when reaction from the restraint from the from the added support is taken into account. Okay, so the support here is the support that we add to prevent side sway. Okay, it's not there. This is our real frame. There's no support. We just add this so that we can calculate the moment due to the load alone. So see here is add that to prevent side sway. Okay, so that means without this, we don't have sigma fx equal to 0. With it, we have sigma fx equal to 0, which in turn, it means that this frame is actually being pushed by this unseen load. So we can say that it is as if this frame was, because as if, you know, it's past tense, was pushed by this 0.82 load. So you can say the moment, therefore, it is this load that will lead, that will lead us to moment due to side sway. Okay? Still, you know, case number 2 now. Moment due to side sway. So now we know that this frame is under the 0.82. Okay, now you need to analyze this frame as if it was being pushed to the side by this 82 load, which comes from this. Okay, but again, we know the load, but we don't know how much. Still, we do not know how much delta or FEM is. I was gonna write the question mark. Okay, still we don't know. So we have to assume something now. So assumption is required. Okay, now we are going to make our assumption, but again, we must make the assumption based on the true relationship of the frame as well. This frame, if it is going to sway, the delta here will be the same, and therefore it is likely that the moment to resist the side sway should all be the same. Okay, so let's say the assumption must be reasonable. Okay, so let's say I assume that my end moment here is going to be minus 30. Assume this. That means this has to be minus 30 because it's the same for the member. Then from this member to this member, because the displacement is the same and the stiffness is the same, so this better be, you know, minus 30 as well. Okay, so that becomes our fixed end moment. So after the assumption is made, carry out moment distribution as usual. Because once you impose this minus 30, you know, on the frame, this become the unbalanced moment, right? So you carry out your moment distribution as usual until final moment is obtained. And after this, we obtain this result. Let's say the final answer here is minus 24.4. This is minus 19.4. This is 19.4, 19.4, minus 19.4, and of course, minus 24.4 here as well. And guess what? You can again calculate the shear. Let's say here. Okay, what did I write? Okay, I use the red one. So again, you can calculate the base shear here. $2.19 and then 2.19. Calculate the base shear. So now you know you have 2 of 2.19. So what does it mean? This means the moment here is the result of the frame being pushed by the 2 multiplied by 2.19, which is 4.38. Or here, 4.38. So, in other words, the end moment that you assume will bring you to this. And these are the numbers based on the load that is equal to 4.38. If your frame is pushed by 4.38 kip, this is your end moment. But from part 1, it is known that the frame was pushed by the imaginary, so to speak, load of how much? Oh, what's the number? .82. So let's say, simply put, we need to assume the number and hope that we would hit this number. And so we want 0.82, but we have the moment caused by 4.38. So what do we do? Luckily, well, let's say you need moment caused by 0.82, but instead you have moment, oh, fan keeps blowing everything, excuse me. You have moment caused by 4.38. Luckily, you live in the elastic world, okay? You are in elastic world. Which means the moment due to load equal to 4.38 should be proportionate to the moment due to the load caused by 0.82 kips. So that means that, that means we can use ratio. Okay? Let's say I'm trying to make it very, very clear here. I hope it helps. Okay? So, if moment due to load of how much? 4.38 is multiply by, you want load, you want moment due to 0.82, right? So you must multiply it by 0.82 over 4.38. If moment due to load of 4.38 is multiplied by this, moment due to 0.82 is obtained. Okay, so I can multiply this chunk, just a minus 19.4, 19.4, 19.4 minus 19.4 minus 24.4 minus 24.4. If I multiply this by this ratio, I would get this. Minus 4.56 minus 3.63. Here is 3.63. 3.63 minus 3.63 and minus 4.56. So it's simple as that. It doesn't matter what you assume. In the end, you can always adjust your value by using the ratio, because we are assuming that our structure behave elastically. So this is moment due to 0.82. So voila, now you have the moment due to the load and moment due to sine wave. So step number 3, we combine them. So that means in the end, you have this. Moment due to, let me see if I use the, what color? Okay, it's black. It's this one, right? $11.8 here. 23.5 minus 23.5, 12.7 minus 12.7, and then minus 6.3, and then this one. Minus 4.56, minus 3.63, 3.63, 3.63, minus 3.63, minus 4.56. You just combine them. And in the end, you're going to get your final answer. 7.2 here, 19.9 minus 19.9, 16.3 minus 16.3, then minus 10.9. So this is your final answer. This is your sine wave moment. And then this is the moment due to load. Okay, that's it. Question. It's just a new concept to allow you to break the moment due to sine wave into, you know, another category, and then you deal with it, and then in the end you just add them up. Okay, so is there any question? No questions, so I'm just gonna stop the share and stop the record so that you may feel better. You wanna ask something off the record again, okay?